Hi, everyone. We're the Autonomous System Infrastructure Group. I'm Tej, rising junior at Rutgers.
I'm Steven, sophomore at Rutgers.
I'm Pranav, a rising senior at Manalapan High School.
I'm Meghna I'm a senior at Rutgers. I'm Arunima, I'm a rising senior at Princeton High School. I'm Suhani, I'm a rising sophomore at the Middlesex Academy. So the goal of our project was to develop a program that would allow for control of self-driving robots in a smart city environment. And for this, we used ROS as our operating system and PyTorch for the torch library. So this is a robot that we used, and we used this instead of a smaller robot because it was easier to develop programs on it with ROS. And that's the Orbit Smart City environment, which is also behind you, and it's modeled after an actual street in New York. Data acquisitions for ROS. ROS stands for Robotic Operating System. It's a set of software tools and libraries. It helps to build robotic applications. As you can see in the diagram here, we use different components to extract data. These data are image data that are extracted from Wilson's cameras that is mounted on the robot, as you have seen in the previous slide. And the second data is the steer or the twist data that is extracted from the remote control joystick. Then these data are fed into the CNN model, which we will further discuss in our presentation. These model gives out the output steering commands, which helps the autonomous robots to drive.
So we were talking about data acquisition. So the first 2 weeks, first 2 to 3 weeks of our internship, we spent our time adjusting to learning how to use ROS, specifically with just router and publisher nodes. This basically refers to having access to the data, but specifically the image and steering data. And then afterwards, during the third week of our internship, we get a presentation on ROS. And after that, we then to collect movement data specifically, we had to make data. And so to do this, we connected this joystick to the robot, which you may see behind you, I'm not sure. So we connected this robot to the joystick to a robot, and we moved it around the orbit city environment behind you. And so we recorded the movement data, which specifically was the angle we turned it at, as well as the direction. And so while we're also recording the movement data, we also recorded the image data by using the GeoSense camera. And so this diagram here basically explains the process of recording. We have a joystick, get access to its nodes, we convert it to usable data, and it published ROS RA data, which refers to movement data, and thus the robot was able to move on our command. We then took data from the camera, and together we put it into a ROS bag that basically contains the files containing our training data. And this is important because the image data is what we're going to use to train our neural network, such that the system will be able to recognize an image and be able to have its respective movement. So an example is that if the robot is near a corner and the image is recognizing a corner, then respective movement would be to make a left or go straight ahead or make a right.
So in this corner here, you can see we have taken the image from the perspective of the camera that is mounted on the robot. And the video here shows the perspective of the operators. Here you can see using the joystick remote controller, we could control the movements of the robot in the smart city environment.
All right, so convolutional neural networks. So CNNs, also called convolutional neural networks, are widely used deep learning algorithms that essentially are used for applications such as image recognition and classification. So typically there are 4 different layers in a CNN model. We start off with the input layer, which essentially takes the input and feeds it into the neural network for further training and testing. So in our project, our input data was essentially the images we acquired from the RealSense camera on our Pioneer robot. And we have a convolutional layer next, which is the main building block of a CNN model. Essentially takes in the input and transforms it. Transforms it in a way to transforms it and acquires the necessary features for model building. And we have pooling layer, which is optional, but we used it because it essentially reduces overfitting and improves model performance. And we have an output layer, which essentially takes the input from the layers in the model and directly outputs a prediction. So in our project, the output were the steering commands for the robot. So as we can see, this is on the right. It's an overview of CNN model. So it closely resembles the model we built. So we have the input, we have the 3 convolutional layers, and for each convolutional layer, we have a pooling layer, which essentially compresses the image data. And so in the third pooling layer, and third and final pooling layer, we essentially flatten the image into one dimension, and we pass that image into a fully connected layer for an output.
So once we acquired the data from the Intel RealSense camera, we obviously have to train the model so that it can recognize when to do what. So to do this, we wrote a custom data loader class to train the loading data into the model that we acquired through the camera. And then after that, we built a training class to train the model based on the inputted data that we got. And then we saved the weight files. So these are actually values that are used to transform the inputted data, which are used in testing the CNN model. So once, let's just say, for example, we get an image of a corner, as Steve was explaining, after training the convolutional neural network model with different images, it'll be able to recognize when to make a left turn or when to make a right turn, which we can use in our autonomous system movements.
So some future work that we'd like to do. So first, we were working on the robot, which is kind of large for the orbit environment because it doesn't properly fit into the lanes. So we'd like to implement what we've been working on into a smaller car, like the one made by the Mini Smart Car Group, which can make easier turns around the city and fit into the lanes properly. Also, most of our project, we've been working on creating autonomous driving in a simple loop. So if you put the robot or the car in any part of this loop, it can keep going around the loop. So we'd like to work on implementing the data acquisition and the neural network in more complicated environments, such as if it sees a traffic light or a stop sign or a closed pedestrian.